Hello everybody, my name is Connor Thompson and this is my Lab 2 report. Lab 2 is all about observing the parabolic motion of objects at speeds that can be impacted by external forces, so in our case it was gravity and drag, and then we analyze this data through observed means with the tracker program or with predicted models such as GlowScript code. This lab primarily deals with concepts in net force, velocity, position, displacement, drag, gravity, and then modeling these concepts with two GlowScript models based on drag and no drag. And the idea of a system versus surrounding, so in our case the system might be a paper ball thrown object with parabolic motion, and the surroundings might be air that's acting on it in terms of drag. Before we go any further, this was my result. So this is a screenshot of the tracker program. You can see the traced path of the paper ball as it moves, thrown midair, which is important for later. And then this is just the x versus time position, the y position versus time right here. This is the code that was used in GlowScript to make the two models, drag and no drag. I'll go into what these red lines mean later, but right now all I need to know is this is the code. This was the models produced by the code. So this is with no drag. So you can see it has this nice parabolic shape, just acting in terms of gravity, pushing it down. Well, this has drag as well, which is pushing it back a little bit because of the drag acting against the ball this direction. This was the Excel graph made. So you can see the blue dots here are the tracker dots. As it moved, you can see it starts midair like I was talking before. I'll go into the differences later, which are probably errors. This orange one is the code with as no drag, so you can see it's just gravity acting upon it. This is the code with drag. So you can see they're actually pretty similar, except for maybe a shift in position. Now the background of the experiment. So like I said, we have a paper ball thrown in a parabolic path to determine trajectory. The primary equations that were used to develop this coded model were the force of gravity, F equals mg, and the drag force, which is this equation right here. And taking data from the tracker, you can see the object travels about -2 meters per second in the x direction and 2.82 meters per second in the y direction. And then tracker naturally has 0.033 second timestamps that I put in these two uh, paths right here. Now the net force was calculated just by using F equals mg, negative of course because it's acting down, and this was updated by velocity squared times b, which is the drag equation right here. That b value itself was calculated by observing the change in the x component velocity over time, which is acceleration, multiplying that by the mass of the ball to get the force drag, and then dividing that by velocity squared, because they're right here, to get b. The velocity right here is updated based on change in velocity based on F equals ma, of course, multiplied by time to get velocity because acceleration multiplied by time is velocity. And then position is updated based on v equals meters per second multiplied by the time just to get the change in meters. And these assumptions on this code worked out pretty nicely because it produced a parabolic graph that was very similar to the one modeled by the tracker program. Now, as for similarities and differences, like I talked about earlier, specifically in terms of these two graphs right here, this one is up in the air a little bit because it was thrown midair while the tracker graph, or I mean the GlowScript code was modeling it, assuming it was thrown from the ground, which caused these differences here, which could just be like changed by just shifting the graph a little bit. However, if you can notice, there is a difference in the y axis, which is probably due to either errors in the code, formulas that I might have miscalculated, or the paper ball is not a smooth, even surface. It has pockets that could be impacted more by drag, pushing it down more, causing it to be shorter than the coded model. But overall, they're pretty similar, just based on how the code was modeled after real physics formulas. Now, what if? What if the paper ball itself was thrown straight up instead of parabolic in a parabolic trajectory? Now, one thing that's important to note is velocities naturally have horizontal and vertical components. With parabolic motion, there is a split between these horizontal and vertical components that is almost equal, but they're smaller than the vertical motion, which would have it all straight in the y-axis. This means that all of the parabolic moving object has to travel on the y-axis occasionally throughout its motion, well, throughout its entire motion, but just not as much. The horizontal component keeps it closer to the ground than it would be otherwise and helping it reach that ground faster, even with drag slowing it down. Meanwhile, the object that was thrown straight up will have to travel the full vertical distance in the y-axis, decelerate, and then come all the way back down, which takes a lot more time. As for equations used to predict this behavior, assuming distance to reach ground is determined primarily by the y component velocity or motion, not only does the vertically thrown object have to travel more in that regard because of what I just talked about with all the velocity being in the y-axis, it has drag force acting along the ascending and descending parts of that motion, slowing it down. While the parabolic moving object has significantly less drag acting upon it because it has a lot less velocity in the y-axis, meaning it's getting slowed down less and is moving faster. Now, what does it mean? Look at both these graphs. This is the no drag and this is the drag. So terminal velocity is based on no net force acting upon it. But because the velocity is changing and F equals ma, there is a velocity change, which means there is a force acting upon it. However, it is important to note that with the drag graph is tapering off here and approaching at an asymptote at roughly -3.75 meters per second, meaning that it's actually getting to a point where there is no velocity change, there might be no net force acting upon it, which means that there might be terminal velocity being reached. However, if we wanted to change this experiment to actually reach that terminal velocity, all we would have to do is just change the height it was thrown, which means it'll have more position on that downside of the parabolic motion, or like more room to actually fall, reach that point where force drag equals force of gravity, and thus giving us that terminal velocity.